This is our first BAA webinar, so we're all very excited to slightly nervous as well. But we're all hoping that you're going to be able to enjoy this from the comfort of your own sofa, dining room table, or bed. And let's all face facts, there's probably a few of you who are enjoying it. We wanted just to have a quick shout out to our amazing sponsors who you'll see on the screen there that this event wouldn't be possible without. So just want to give a shout out to Alamir, Ipstock Brick, All Good, Armitage Shanks, Taylor Maxwell, Delta Light, McKellen and Company, Marley, Somatic at Kitchen Gallery, Rene's Aluminium and Altro. So thank you guys. So yeah, big thank you to them. And just to give you a bit of an idea about how this webinar is going to go, we have 3 speakers tonight. We've got Rob, Ian, and Paul. And if you want to ask them a question, please do so. We're taking questions at the end. If you have a particular question that you want to one of the speakers, then please make sure you mention their name. And also this is being recorded, so if you do not want to be recorded, please don't ask a question. We won't therefore have any reason to have you on film. So thank you. So let's get this started. First off, our good speaker Ian Goodfellow is a principal at Birmingham and is the practice sustainable lead. He is led on a wide range of innovative and environmental projects and research initiatives, and is committed to the development and communication of genuinely sustainable approach to architecture. Next, we'll have Rob from Web Yates Engineers. He's a structural engineer with a passion for creating innovative, effective, and elegant structures, having designed projects ranging from stone staircases and timber pavilions to city town centres, railway stations, and airports. Having started his career with Arup, where he was brought up on the philosophy of total design, he now leads the Web Yates Birmingham office based in Jury Quarter, where he promotes a collaborative and innovative approach to engineering. He strongly believes that all buildings should be designed with sustainability in mind, making best use of finite resources, and believes that the industry must challenge the status quo in order to innovate. And last but no means least, we have Paul. He heads up the energy and sustainability at Web Yates Engineers. Paul has worked in the field of building services engineering and building physics and sustainability for over 30 years. During this time, he has helped to design many low and zero carbon buildings with particular emphasis on passive design and techniques. Many of these buildings have achieved BREEAM Outstanding and Excellent. So again, want to thank you all for coming to this BAA webinar, and I'm going to hand over to Ian.
Thanks, Matt. I'm just going to attempt to share my screen. Right, hopefully you can all see that.
Yep, that's looking great.
Okay, great. Well, this is an unusual forum, but it's great. So many of you have been able to attend, so thank you for that, and thank you to Matt and all at Birmingham Architectural Association. I thought it'd be interesting just to start. This talk is very timely. We're exactly 1 year, almost by a few days, since the Architects Declare Climate and Biodiversity Emergency was launched, and I believe the Engineers Declare came out pretty shortly afterwards. And so that means that was 10 years then, so we've now got 9 years left to deal with our climate emergency, not to mention the other emergencies that seem to be piling up alongside. I thought it would be good just to start by reminding us of all the 11 action points from that. And I think some are probably slightly hidden here by our faces. But I don't expect you to read through them all, but I just think the overall focus of them is that in addition to the familiar points around carbon and energy, there's also a focus on and a call for a more holistic and systems-based approach to addressing the climate emergency, including the term regenerative design, which many of us have heard in the last couple of years. But essentially, that's a paradigm switch that's being encouraged, and it's really away from doing things less badly to starting to see how we can actually design smartly within the opportunities and limits of our own biosphere. So I think for those of you like me, probably always slightly challenged by the idea of the triple bottom line of sustainability, where we had economic, social, and environmental, it always struck me that economic and social were subsets of the environmental, as we have been living within our biosphere and within our means for many thousands of years until fairly recently. So I thought this talk will cover some of that in the projects that we've been working on together, and probably in essence we'll be covering these ones that I'm highlighting in green. I think the key thing is really this, for this talk, is about the third last one there: collaborate with clients, architects, engineers, and contractor to further reduce construction waste. Well, that should really be about to innovate, to be able to co-create and to find a way out of this tricky situation through ingenuity, imagination, and intelligence that I think we're all hopefully fairly well adept at in our own fields, but it's somehow to build that into a greater understanding and be able to work more collaboratively together. This is a rather wonderful a paradigm kind of diagram produced, I'm not sure how many of you will have come across this, by Kate Raworth on donut economics, and that's very much about establishing and working within our limits, within our ecological ceiling, as she calls it. And I think that's another indication of this move to a more systemic way of thinking. And actually, I heard the other day that the city of Amsterdam, rather than this just being pie in the sky, Kate has been invited by the city of Amsterdam to help them develop their whole future development plan around donut economics. So that's the beginning of a shift. The RIBA, the 2030 Climate Challenge, came along last year after the government's commitment to 2050. This is about trying to, for architects and engineers, the whole design team, to achieve as best as possible these 4 points by 2030, but ideally sooner. So we, as a practice, Pinar and Prasad, we've been very much engaged with sustainability since we did the design competition for this building back in 1995 for a very enlightened client at that time in the borough of Barking and Dagenham. They were basically asking for a building that would be touching the earth lightly. It would be, sorry, I'm just looking at some notes here. Yeah, it was very visionary for the time, asking for a building that would touch the earth lightly, minimize impacts in embodied and operational energy, and be designed for end-of-life disassembly. So I think this project exemplifies for me something of our approach to architecture, and I think the sustainability agenda has helped to further galvanize that. And it's really quite a distinctive collaborative design process where we've been co-creating with our clients and design teams really long before the term co-creation came along and became such a buzzword. And I think that what we achieved on this building was really the coming together of client and a very inspired design team, engineers and mechanical electrical engineers, to come up with with innovations that helped to meet this brief, that also asked um, for a building that would be able to be designed for end of life disassembly. One of the innovations, for example, was this is a very contaminated piece of land, and this was a lightweight building, really to deal with quite a peripatetic use in terms of the park rangers coming and going. It didn't need to be used all the time, so it needed to be able to be heated up quite quickly. So it wasn't high mass. And we looked at utilizing helical screw anchors, which had only been used up until then in the United States for tension for tethering large electricity pylons. So an innovation here was really to find that we could actually use by it being quite a lightweight building, the bearing capacity that we tested for these helical screws, we could use these as foundation piles. And each one, all the piles went in within one day. We didn't need to mess around in contaminated land. And we didn't leave a giant legacy in the ground of many tons of concrete. So it was addressing the embodied energy in materials back then. So really, since then, all the way through to 2020, we're now working with UCL on this rather crazy big laboratory for a mad professor. I hope Nick doesn't mind me saying that. Really based around the design of platforms and rapid transport, etc., but also around very people-centered design. So it's working with neuroscientists and a whole range. Again, this theme of collaboration that keeps coming up. Here, it's a whole team that the Professor Nick Tyler is drawing on within UCL in his research, and they'll be housed in there alongside the large-scale experiments. The building is zero carbon in use because it's basically a large shed with a very big roof, and therefore we've got a full covering of photovoltaics that achieves zero carbon in use and beyond. That's obviously a fairly simple way of addressing zero carbon, and we know that that's not really tenable on all projects, but at least UCL were prepared to put their money where their mouth was and go that extra mile to fund the PVs. Through that journey, we've also designed a number of other developments. This one, BREEAM Outstanding Carbon Negative Development in North London. It involves a heat and power network, local heat and power, and it's really achieved zero carbon. This is approximately 10 years ago. This was developed by exporting the extra heat that's generated in the electricity generation off-site to heat Islington-owned properties, housing blocks, which had previously very poor high carbon boiler systems, which we were able to replace with something much more efficient. That network can be extended in the future, so it's about growing these networks. So right through to also a project that we did with, one of the projects we've done with Web Yates, so we'll be talking about today. This is the new studios, Wimbledon College of Arts, where we had a very enlightened client that asked for a sustainable building, but then we took that to them and we pushed for it to go to BREEAM Outstanding, and they were prepared to go there, obviously provided it fitted within the budget, which is always a bit of a challenge. But I think in learning about this building, you'll also learn that we managed to square that circle and do a fairly low budget building and still achieve BREEAM Outstanding. Here it is in its context viewed from the adjacent playing fields. And it's a building that very familiar to you. Many of these moves, we actually, through the orientation, actually the site lent itself well to good positioning. Further passive measures, really maximizing passive measures, which I think is a big message from today. And then only after that, looking at how we could actually put in the most efficient systems, and then the renewable energy of photovoltaics on the roof. Key to all of this, though, was thinking about the building fabric. It had to be built very fast. We wanted essentially a building that would be low in embodied carbon, but we were also wanting to get that to maximize the benefits of thermal mass and nighttime cooling to be able to make it more climate resilient, establishing these comfortable internal temperatures that don't fluctuate with that one gets with the lightweight building. So this, working with Rob and Paul, we came up with a hybrid solution where we're using timber and timber to support what are then concrete slabs, but these slabs are only 50 mil thick, so that we're able to get all the benefits of nighttime cooling without a massive high carbon concrete frame. We then looked to how to achieve that in the walls, and this detail shows that we were actually using this high density fiberboard, 4 layers of it, all the way around the perimeter to give us also thermal mass in the walls. And that's then led to this very elegant solution that Rob and Paul will speak in more detail about. But it's a very versatile building. It at its time was probably one of only 4 hybrid buildings like this, and you could say it's slightly arse about face to begin with, thinking about it, because you've got a timber structure supporting concrete, but actually we're only using a minimum of concrete to achieve this thermal mass. This then gave that was like the baby brother to this project. That was the next one that we did as a team together, again with a timber frame and with the concrete, but a much bigger building that Rob and Paul will talk in more depth with. But I think what I'd like to say here is that establishing relationships is vital, and it's something that is often tricky to achieve with procurement routes and all the rest of it. But it makes so much sense. Once you've found a group of individuals that you love working with, why wouldn't you want to work with them again? And often we struggle a bit to do that. So it was fabulous to be able to work again with them on this project. I wanted to show just one more project, which is really about reuse. I think we've talked about new buildings a lot, and I think we often focus maybe our thoughts a bit too much on new buildings, but we're really going to only solve the huge problem we've got by also looking at the existing stock, both domestic and non-domestic. And this feels like a good case study for that, because there is an extension, there's a modern part to it, which is right at the far left of the photograph, but there's also a reworking of the old entrance and the core of the building. It's a library for the University of Kent. The brief was for this extension and for helping to sort out some of the problems they had with the existing building. And our submission was one of the only ones that actually kept the entrance where it was and not move that into the extension. And by doing that, we kind of helped the university to slightly swallow the bitter pill, but the one that would allow the existing building to be transformed and to be able to be useful for a long life ahead of it. This is the extension. And on this, we played all the things we possibly could in terms of passive measures. With a new podium to the south, we buried in there ground tubes. They then bring cool air into the auditorium, into the lecture theatre, and then that has the option in the winter of heat reclamation, otherwise exhausted out. And we have a whole array of north-facing roof lights that allow ventilation and a lot of light into the depth of the plan. And also with a mixed mode building, it really maximizes the openable area of the external facade. So you get a lot of light in from all sides, and actually the building really breathes in summer, and in the hot summer that's just been, in fact, it was very cool in here. I did look for a photograph without the lights on, but this is a typical thing in all of our buildings that we design to be very low energy. Often we find that the sensors, things that are non-human interfaces, often are the things that go first, and you end up with battling against lights that remain on all the time, etc. So that would be one lesson, is to always make sure there's manual override on any of these systems. This is the core of the building, and we analyzed this in close detail, and really chose to do one key bit of strategic work here, which was to remove the structure here. The entrance facade and half of the floor plate in one of the spaces above the entrance. It was very pokey before, you couldn't see where you were going, and we transformed it into this, so that on arrival you immediately have wayfinding. You have a large space that works in terms of ventilation very well, and wherever you are on the upper floors, rather than just being lost in an endless library of floor plates, you come back past there and you immediately recognize where it is you came in, and you have this great sense of wayfinding. Very quickly, just to conclude, I think now with the emphasis on more systemic thinking, I think all of these things, biophilia, for example, has come in much more strongly. This is a real hero of mine, E.O. Wilson. He's actually the world's leading expert on ants. You can see the large ant hill behind. And Paul, in fact, is going to refer to some of the work that he did around the study of termite mounds. He discovered how ants communicated to one another. And he also analyzed lots of things to do with human behavior, which relate very much to our talk this afternoon. Here, circadian rhythms, we're discovering that, yes, 24/7 is all great, but actually we're also tied into some pretty fundamental aspects of natural light and its complexity and how our body registers that. And lots of these things are then being picked up into standards such as the Well Building Standard, ever more complex to represent this complex systems thinking. But we shouldn't get bogged down in the complexity of it. And I guess the Green Building Council have been doing great things in terms of circular economy, which you could say is a first step to addressing things more systemically. And I think many of you are familiar with this, linear economics going into reuse economics, eventually into circular economics, where that's then taken a step further into looking at a biological cycle and an industrial cycle, and making sure that where appropriate, these things are kept apart, and where they are brought together, that things can be recycled out separately, so that one lot returns to within the natural cycle, within our living systems, and the other within industrial life cycle. And this whole thing of circular economy, then we're using very much in our new building for Moorfields Eye Hospital at St Pancras that we're currently designing, and back to the crazy shed for UCL for all the big experiments. And I'm now going to hand over to Rob. Thank you.
Thank you, Ian. Oh.
Okay, can you see that, Matt?
I can see that, but I can't see you.
Ah, yeah. Let me. I'll get myself back on here. Just bear with me a second, guys.
Rob, if you go to the top of your screen where it says you are viewing, here, it should pull down a menu that allows you to turn on your mic and camera, I believe.
Yeah, as most people know me, I'm not the most au fait with technology, so I can't find that button, and I've lost my thing. But if you can still see the PowerPoint, I think we'll probably better just roll.
We can still see the PowerPoint. It's all good. Thank you, Rob.
Excellent. Apologies for that, guys. I'll save you having to look at me for the next 20 minutes. So yeah, thanks a lot for that, Ian. I think I'll echo this is, it's great that everyone's kind of come together to hear this, but it's also quite an odd environment to do it in. So, but also quite exciting as well. So let's see how we go. So yeah, I'm Rob Neal from Web Yates Engineers, and I lead our Birmingham office, which is based in the Jewellery Quarter in Birmingham, and I'm a structural engineer. A bit of background about us. We're a 60-strong multi-disc engineering practice with offices across Birmingham, London and Bristol. The company was formed back in 2005 with the founding director's aim of pursuing intelligent and adventurous design. And we deliver projects across a huge range of sectors, and we're also proud to work on projects of any size, literally from a garden shed to a £200 million infrastructure project. Here's a garden shed, and here's the Kilo box, which is a 200 metre by 100 metre basement box in the middle of the taxiway at Heathrow Airport that's currently under construction. And it's our wide range of interests, I guess, that allows us in our shared philosophy of collaboration, which allows us to push the boundary of design in our projects. We've got a philosophy based on rationality and integrated thinking. And in every project, we want to explore what is truly rational rather than just adopting industry norms. So we think about how the structure and the services can work together to make the building better for the user, and how these elements become the architectural expression rather than something hidden behind the finishes. And as you'll see, we've got a strong emphasis on materiality and aesthetics. We really think about how the material and the form can affect and complement the finished building. So to explore our approach to sustainability, we'll be looking at energy and carbon. Building on what Ian was saying about the construction industry, it's responsible for about 40% of global carbon emissions. So we as building designers have got a huge responsibility, but also an opportunity to reduce this. And for years, the emphasis has been on the reduction of operational carbon. But unfortunately, the embodied carbon of a building on day one is now the elephant in the room, with up to 25% of a building's life cycle carbon stored in the actual structure. So we've got some serious work to do to reduce that. Just wanted to show you a typical breakdown of some average buildings. So looking at an office, a hospital and a school. And from this, you can see that between the substructure and the superstructure and an allowance for construction of those elements, that makes up around about 70% of the total embodied carbon. So how can structural engineers make a real and purposeful impact to this? So our two main tools are material and form. This chart compares the thickness of beams of different materials supporting a 1-ton car over a 2-metre span. So from left to right, we've got timber, we've got engineered timber, concrete, steel, and we've also got stone in there. Comparing strength, timber is the weakest, needing the thickest section, with steel about 20 times stronger, needing comparatively less material. However, we also have to account for the stiffness of the material, which is how much it moves. And comparing long-term values of timber and concrete, you actually need less timber to do the same job as concrete, because concrete's not actually as stiff as you might think due to long-term shrinkage and cracking and things like that. But the bottom line here is probably the most interesting in this context, which is the embodied carbon per metre run of each beam. And you can see that for timber, although we need more of it by volume, the embodied carbon is about 4 or 5 times less. Added to that, the green boxes at the bottom is showing the amount of carbon that the timber sequesters during the growing cycle. And so long as it's reused after the building life and not burned down or left to rot, you can use this negative carbon to offset the overall carbon footprint of a building. So if we're to make any difference really to carbon emissions, just based on these simple metrics, we clearly need to build more with low carbon materials, timber, stone, and less with the high carbon materials such as concrete and steel. Now, we can't avoid the use of concrete. It's actually very useful as a material, and it does have its place. So we've always got to think about the form as well. This ribbed concrete slab uses about 60% less concrete than a standard flat slab of the same span. So that's less embodied carbon, but it's also 60% less weight going down the foundations as well. Speed and convenience on site have eroded this form of construction, but it's making a comeback. Now, none of this is new, of course. Some of the most impressive structures through history were born out of austerity and material scarcity. So you've got Pierluigi Nervi in Italy in the 40s, who was producing fabulous, beautiful ribbed and vaulted roofs using bare minimum concrete and reinforcement. And in Ilario d'Este's doubly curved post-tension structures, which made good use of locally made bricks to create the vast spans that he did in Uruguay in the 50s. On a different scale, here's a small project we did, which is to install a new mezzanine floor in an existing property. And here we used cast iron formed in 3D printed molds to create traditional sand molds, which created a form to follow the stress line of the plates to minimize material, but it also became the theme, the architectural expression of the structure. And what's great about this, it's these smaller projects which become the test beds for new techniques, which allow a bit more freedom and experimentation to prove a concept before scaling them up. So Wimbledon College, the project we collaborated with Ian and his team on, like Ian was saying, the scene was set to create a textbook naturally ventilated building. They cleverly arranged the building to take full advantage of the north lights, which gave great levels of natural light to the studio space, but also created large expanse of south-facing roof to house the PVs. So internally, there was no real aesthetic intent except a goal to provide thermal mass to provide passive cooling to the space. So rather than just use a standard precast on steel frame or cast a flat slab, we questioned how much of the concrete was actually mobilized for the thermal mass, and we found the answer was about 50 mil. So we kind of turned the question around and said, if we provided the minimum amount of concrete to provide the thermal mass, then what was the best way to support it? So what we came up with was this. It was a hybrid timber concrete structure where we combine the low carbon properties of the timber with the high thermal mass of the concrete and tune the quantities to get the required overall performance while minimizing the embodied carbon content. It's relatively cheap and simple timber frame, actually, 75 mil thick precast planks, spanning around 900 mil onto glulam beams. The concrete plus the screed provided the required acoustic and fire separation. The timber was exposed, so it used the sacrificial method for fire protection on the lower floor. And also the ribbed effect did something towards acoustics and negated any need for suspended acoustic treatment. But most importantly, the concrete along with the walls, which were clad internally with a cement particle board, that all provided the sufficient thermal mass to negate any intervention for cooling at all. One of the things about when you expose the structure, you have to have fine attention to detail, and we did countless sketches and options to refine the details to make sure that all the exposed connections were seamless. And we also worked with Paul and his team very closely to make sure all the exposed surfaces were well coordinated. And yeah, so an ambitious scheme, but through the open-mindedness of the client and the spirit of collaboration between the design team and also the contractor, who thought we were a little bit mad at first, we were able to deliver this unique building, and it was one of the first timber concrete composite buildings in the country. So when the next project came along, another collaboration with Prannoy and Prasad, we decided we'd try and build on the lessons learned at Wimbledon and develop the system further and further refine it. So the Anna Freud Centre provides research and training facilities for the Anna Freud charity, and it was part new build, part refurbishment, located on a tight site in central London. It's got a large basement and 6 stories above ground. So one of the keys to this was being able to reanimate the existing structure and reuse it. So that's truly sustainable in that context. We cut away floor slabs, creating double height spaces. We moved the lift shaft. And by doing this, we were able to reduce the amount of new build that was required. Then for the new portion of the building, we worked again closely with Ian and his team, Paul and his team, to produce a refined version of the Wimbledon scheme. But this time we used a relatively new engineered timber product from Germany called Baubuka. Baubuka is a laminated veneer lumber made out of beech, which is a hardwood. So overall has a much higher strength than glulam, about sort of 2.5 times the strength, which means we can use less of it, and the member sizes can be smaller with larger connection forces going through, so a bit more flexibility. We also investigated making the concrete plank work constantly with the timber. Very much the same philosophy as a traditional office building, where we use shear studs to provide composite action between steel beams and concrete slabs. Here, to achieve the composite action, we use 12mm coach screws, and these were screwed into the top of the timber before landing the planks on the timbers and completing the detail with an in-situ concrete stitch to really stitch all those connections together. We did extensive research at the BRE, did some mock-ups and tested them to failure to get all the data we needed to justify the design. And yeah, it kind of resulted in a holistic final solution, which was both structurally and thermally efficient as it could be. And the end result, it's got a similar calming aesthetic to Wimbledon, with the exposed concrete and timber sitting quite nicely together. So this sort of aim to reduce embodied carbon, we have over the last few years been calculating the total embodied carbon for all of our projects. So we're now able to compare projects of different sizes, typologies, materials. And this graph shows the total embodied carbon per metre squared of each building, with each bar representing a project and the different colours representing the different materials. So you can clearly see the concrete, which is the lower red portions, and this figures heavily as most buildings, regardless of their superstructure material, will generally have concrete in their foundations. You can also see where we've got large amounts of steel, where we've got a steel retail building and a largely steelwork project at an airport. The green is the relatively lower contribution from timber. So even where we have a full timber frame, it only amounts to quite a small proportion of the building. And we've also noted on there under the zero line, the sequestered carbon, which is counted separately as a negative figure. Then all the non-structural stuff, so the facade services and the finishes, are the dashed portions above, so that you can understand what the total embodied energy in a building is. So where do these sit with industry benchmarks? So the RIBA produced a set of target metrics that they reckon we need to meet by 2030 in order to limit the carbon emissions sufficiently to limit global temperature rises to 1.5 degrees. So the bottom table here for non-domestic buildings, the current benchmark is what is now the 2020 target, which is 800 kilograms of CO2 embodied per metre squared. This reducing to about 500 by 2030 to meet the targets. So if we plot these lines on our previous graph, we can see how we rank. And to be honest, it's not too bad. We're generally comfortably within the 2020 targets. And in many cases, we're within the 2030 targets too, which is encouraging. Wimbledon, the highlighted project on the left, is there at about 350 kilograms a metre squared carbon. And Anna Freud, despite large concrete basement, is actually quite low at 500. And a lot of that is helped by the refurbishment of the existing building, adding to the floor area. There's another project we're currently working on, a synagogue in London, which is down at about 275. And it really shows by making sensible decisions at the outset and setting clear sustainability goals, these low values are achievable. And it's also clear by using low carbon materials, reusing existing buildings, we can reduce the overall carbon footprint and try and bring the planet back within its limits. And I think as building designers, it's our collective responsibility to push to do this. So what about the future and future development? One avenue is actually looking into our past and the material that's been used in buildings successfully for thousands of years. If we're looking for a reusable material that's strong, robust, beautiful, then stone is ready for a revival, we think. Its compressive strength can supplant many concrete and steel applications, and the bending strength, although not in the same league as steel and timber, is still substantially higher than concrete, and we can use that to our advantage. So if we take a step back and think about how we make concrete, we take our fresh stone at 100 newtons, we crush it for aggregate, we burn it, we grind it to make cement, we mix it back together into a paste, we deliver it to site where we've built our false work and formwork, we've added a load of reinforcing steel, We pour it into the molds, wait a week, and hey presto, we've created something that's only less than half the strength at 40 newtons. So over the last 10 years or so, we've built up a knowledge base and expertise, including methods for testing, design, and specification of stone. We started out really from doing stone staircases in Georgian mansions in Mayfair. And this has grown through collaboration with some key stonemasons, Stone Masonry Company being one, into some of the applications that we are using today. This building is Clerkenwell Close in London. So rather than having a concrete frame clad with stone and all the complicated fixings that come with it, it's got a fully load-bearing stone exoskeleton instead. So internal concrete slabs span out from a circulation core. They're vertically supported through firmly broken connections onto the stone columns. Each column is sized appropriately for the load on it, and also the minimum amount of machining. So the original drill holes, saw grooves, and even fossils are visible on the surface of the stone to give it a real kind of raw character. So this is a traditional vertical load-bearing application, but we're out using it for a spanning element, so a floor. So we've also done a lot of research and design with post-tension stone. So borrowing a technique from the concrete industry, by adding some thin steel strands and adding a tensile force, we can lock the stone together in compression, so that under bending, the tensile forces developed aren't enough to overcome the pre-compression, which gives it the ability to span. And also the high compressive strength and stiffness of stone make it very well suited for this, unlike concrete where you have to put an additional reinforcement to deal with long-term effects. So an application, this here's a test stone bench we did, which has something like a 3-meter span, an overall depth of 50 mil, with a span depth ratio of about 60, which is super thin. Normally for beams, you're looking around 15 to 20. And taking this a step further, after we'd done a number of straight post-tension stone flights, someone wanted a spiral stair. So this is a 330-degree helical stair, each tread individually cut, a pair of 30 mil post-tensioning cables, pre-stressed about 15 tons each to create this. So the stairs might look nice, but not much use for a school or an office floor. So one of our latest research projects postulates a 30-story tower, 12-meter spanning open plan floors made entirely from stone with a load-bearing stone exoskeleton and internal stone floors. So here it is superimposed in the City of London at a fraction of the carbon of its neighbours. So just to prove that this isn't complete pie in the sky, to test this concept, we built a prototype section of floor. And this is currently erected outside the building centre in London, so you can go and see it, to demonstrate a typical 12-metre span. It's 450 mil deep, weighs 7 tonnes, and it's actually shallower and lighter than its concrete equivalent. Unlike the stair, it's formed from small blocks of stone with 16 mil cables installed through pre-drilled holes, and it's just pulled tight with a small hydraulic jack to pre-compress it. And so in terms of embodied carbon, inherently stone has 0 carbon footprint. It's the energy used in quarrying, preparing and lifting the stone into place really where the CO2 builds up. So typically, if you went for a fully stone superstructure, you'd save in the order of 70 to 90% of the embodied carbon against its steel or concrete equivalent, which would be a considerable saving and would far exceed all the previous targets we've been looking at. So I'll end on that one and hand back over to Paul, and hopefully he has more luck with sharing the video as well.
Thank you. Thank you, Rob. Paul, if you hit your video first and then share the screen, then I think you might. Yeah, there we go.
You got me. Hi, everybody. I'm probably less adept at this than Rob. So you just have to all bear with me a moment.
It appears like we've got the blind leading the blind around here.
Bear with me a moment whilst I just get myself.
That's
yeah,
fine.
We are. I think I'm pretty well there, am I?
Great. Can I just say quickly to all the attendees, thank you so much. A few of you started asking some questions, but if you do have any questions for the panels, please do ask them, because after Paul, we'll be going to questions. So thank you, Paul. You all sound good.
Great. Thanks very much. Well, good evening, all, and welcome to you all, and in this rather sort of strange event that we're involved with here. But it's all been very interesting to me so far. Thank you, Ian and Rob. That was pretty thought-provoking there. Thank you. So now we're going to have a look at how, with a bit of collaborative design, we can eliminate or at least minimize in-use carbon emissions. Just to say that I haven't had time to go through, I won't have time to go over everything that relates to the carbon emission use, but I've tried to concentrate on the key points. And I think we can probably pick up any further issues that you want to discuss during the questions. So, carbon in use, where are the emissions? So within the main built environment, what are the main components? Then we're going to look at comfort and how that specifically gets involved with carbon emissions. And then we're going to go into how we can best reduce emissions in use and create zero carbon buildings. And then we'll pick up on a few examples from the earlier reference projects that we've collaborated on. So here's a very familiar looking chart. I'm sure you've all seen this kind of thing. It's what is spat out from a dynamic model created for the purpose of compliance with building regs. This is in particular for a mixed-use development incorporating residential and retail and some commercial. The pink bar on the left there is indicative of the target emission that's required to achieve a building regulation compliant building. The B-lean bar in the center, green bar, is what we're achieving in terms of emissions once we've applied various fabric improvements and energy improvements associated with equipment. The furthest green bar, the big green bar, is the reduction that's achieved once we've applied any renewables, photovoltaics, solar panels, etc. And what I've added in on this, and it's more for interest than anything else, we're not really going to be looking at this in detail, but the gold element of the bar is the actual sort of plug-in items, computers, cooking, general appliances. You can see that's quite a significant bulk of the emission within a building, but that which we don't really have control over as designers currently. So what does that look like globally when we look at it from the built environment as a total? So it's estimated, these are UK green building figures, by the way. It's estimated that the contributed or the attributed element of to the building environment, or the built environment, is 42%. That's then associated with a 22% value, which relates to the operational and sort of embodied element of carbon. So with that operational, we're really looking at how we comfort control our buildings, how we make them comfortable for us to work and occupy. And that's one of the areas I'm going to move forward and concentrate on. But before we do so, I'd just like you to bear with me a little. I'm sure you probably are all fully aware of this kind of stuff, but I want to go back to some basics, and I want to show you firstly how nature deals with keeping a space comfortable. So first of all, the Barossa termite. These termite mounds can reach as much as 4 meters in height. That's partially to achieve a stack ventilation system. The core area of the termite mound is maintained at an average temperature of around 30 degrees. The stack draws air through tunneled vents into the chamber, which then cools the core space. So looking at that in slightly more detail, and please take note of the fins, the radiant fins that actually radiate heat from the core into the air path, so affecting the central core at the 30-degree temperature. So now we're going to move on to sort of historically how humans have dealt with this. And firstly, this is an ice pit. I won't attempt to pronounce the Iranian name for it. These go back to sort of 400 BC, so some time ago. They were used to both create and store ice through a very similar principle that the termites use to keep their space at a reasonable temperature. So drawing air in through the ground mass and exhausting it out through a hole in the top of what is basically a stack. In this way, they were able to, at night time, create ice, obviously during the winter period. And during the summer, using both that principle in terms of airflow, but obviously the thermal mass from the construction itself, both absorbing heat during the day, but then retaining the coolth within the mass through the nighttime vent process. Then looking at actual historically occupied buildings, we just move over to Iran again. This being a house designed in the 19th century, now actually a museum. This is in the city of Kashan. Using a similar principle again, we're drawing air in through basement areas and then exhausting through the vents at the top of the building. And if you look at the interior, I think you probably know there's not a duct or a galvanized box in sight. And so very much passively designed with very little requirements for engineering services. And then just to bring us slightly more up to date, this is a school in India, Rajasthan. It's designed by Sanjay Pure Architects. It's a completely naturally ventilated school and achieves obviously internal environments that enables education and the kids there to work quite comfortably. So sort of why am I showing you all of these spaces in these extremely arduous environments? Well, right. So what I wanted to do was really just identify that we can have passively controlled environments within arduous conditions. So over there in Rajasthan, sort of average, these are average temperatures we're seeing in this chart, average summertime temperatures, that is. So sort of 31 degrees in Rajasthan, in Iran, it's 26 degrees, and oh look, in London, UK, 17 degrees. So actually, we have an environment that very much lends itself to passively, or being passively controlled. Just moving on to the next slide, I just wanted to show where we're likely to be going over the next sort of 40 or so years. We're looking here at some CIBSE weather data, which is considerate of global warming. And we can see the worst case scenario in that period is that we may see a rise to around about 22 degrees in average, remembering that our current average is around about sort of 16, 17. So not a significant rise, but still 5 degrees during the summer period, something we need to think about and look forward and how we're going to deal with in the future. So just before we move to the sort of now and the future, let's just have a look about what have we done in the more recent past. Well, we've, this may be slightly extreme, but we've, you know, looking here at the Pompidou Centre, proudly showing off its attributes. Here we have a significant area of ductwork and services on the outside of the building this time, but that's why I chose the photograph. but what was it really doing? It was, could be argued that it was actually overcoming what were flawed design principles. It's been the case that we build light and fast. We use steel. Steel's been predominant for over 100 years in construction now, and more recently we've created glazed constructions for both working and living in terms of houses, and all of these requiring a significant amount of technical input and technical fixes to maintain reasonable internal conditions. Without those technical fixes, we could quite easily have seen these internals of these buildings achieving perhaps as much as 40 degrees, which is all fine, but the technical fix itself requires an awful lot of carbon, both in terms of embodied and in terms of the in use. We could probably say that potentially we as designers have been partly the cause of having such a significant element of the built environment creating significant carbon emissions. So how are we going to put that right? How are we putting that right at the moment? What are we doing to correct the issues and errors of our past? We are now looking at the use of passive house as a basic design exemplar, and it certainly does work. It works well in terms of minimising carbon emissions associated with heating, and it can create a very low carbon building. There's no doubt about that, and also, you know, timber and low embodied carbon products are used for its construction. The overall carbon for the project is maintained at a pretty low level. But in the context of moving forward with temperatures and global temperatures likely to increase, is a hermetically sealed insulated box the only way and the correct way to move forward? So I think we can use these systems, and they are used very well, but I think there is an alternative or a hybrid to this that we need to consider. So just thinking about our friends, the termites, with their ground cooling system, we can look at and use ground pipe systems. They were alluded to, I think, in Ian's discussion earlier. This is actually a system that we recently installed for a school. So the ground pipes, in this case, they were concrete. That was only because of the ease and cost of purchasing concrete pipes. These are standard pipes that can be used for, usually for sewage, etc. The table there on the left, the graph, is showing the depth of the temperatures within the grass at relative depths. So typically, and interestingly, if we're around about 2 meters, so within the sort of depth of a typical structural zone, we're looking at a temperature in the ground of around 12 degrees. We've done quite a lot of analysis work on this over the years on various projects. This, as I say, was an educational project, and the next graph is quite interesting in the sense that it shows the effect of bringing and drawing air in through those ground pipes in both the environment internally in the building and the air temperature as it moves into the building. So the red line there is showing the external air temperature. We peak in this instance up at 29 degrees. The yellow line is the actual air temperature as it leaves the pipes, and then the various other lines are showing the actual temperatures within spaces of the building, depending upon the orientation. And these temperatures are obviously in consideration of all the internal gains and occupancy levels that are within the building. So you can see that we actually maintain the temperature within the spaces within that temperature or comfort zone. The comfort zone being around about 25 degrees. That's what we're sort of aiming to and targeting at. So it's really how we achieve that level of within a building with the use of, or with the minimum use of carbon. So just quickly, this is the school itself. The hall on the left that you can see is a large performance hall, occupancy levels of up to sort of 300 with those, with the graph that I showed you earlier. So the temperatures in the hall very rarely or wouldn't increase above 25. The building's been in place for some time now. In fact, I visited it recently, and they still don't have it, or they haven't had issues with overheating there, which is a very positive thing. That system not only served the hall, it also served a number of other areas in the school, including laboratories and a sports area. So now let's just move back quickly to Wimbledon Art Studio. I just wanted to do some slightly more detailed analysis here. Just reminding ourselves that this project was in design some 6 to 7 years ago. So some of the values and figures you're going to be seeing in the next slide are not particularly onerous or forward-thinking, but do remember they were 7 years ago. So things have moved on in that period. So we're going to look at various materials and combinations of materials that were analysed to understand their impact upon the internal environment, and with a key view of sort of minimising carbon emissions due to obviously heating and what would have been in place for mechanical cooling if we weren't able to maintain reasonable comfort conditions. So this is sort of getting into the more detailed stuff now. These are the outputs from a dynamic model. So the building is thermally modelled in some dynamic software, and then we can see here that there are up to 12 different materials that were analysed, starting with just timber without any internal lining, and then moving through concrete, which we didn't particularly want to use, but we wanted to understand how alternative materials would compare with concrete. And then we started looking at some more interesting materials, which were fibre composite boards. They were interesting both in the sense that they obviously incorporate a lower carbon, embodied carbon value than concrete, but they're also relatively light, relatively quick and easy to install, which also was part of the brief for this project, a fast installation. So if we look at particularly items 9 and 10 on that, materials 9 and 10, composites 1 and 2, you can see that actually they pretty well hit the mark perfectly. I should just explain that graph at the top there. So we're talking about an educational facility. They have slightly lesser standards than some others. So their actual key temperature is 28 degrees. The black dotted line represents the number of hours that we are able typically to go above that in use. So that's approximately 40 hours. And just to say that we can see there that the materials that were in fact chosen and installed did achieve the criteria we're looking for. The other thing we should say is that the section there, which I think Ian may have had a section of in his presentation, the actual inner lining, which is to the left-hand side of that section, that's where we've installed the boards. So you can see there's actually quite a number of boards installed, but that was determined to be the quantity that were required to achieve the comfort conditions within the space. Obviously, the actual insulation levels on there were pretty high, and we'll just move on to the next quickly, and there we should be able to see. Yeah, so there we are. There's the U values, etc., that were achieved through that construction. Not in today's age, actually, not particularly onerous. I mean, we're now hitting U values significantly below that. I mean, down to sort of 0.1, and even in some instances below 0.1. the permeability level, just to look at that closely, that was good, and I still think we would struggle today, but we achieved actually below 1 meter cube per meter squared per hour in terms of leakage, which is very good, in fact, very good indeed. So what does that result in? Well, it resulted in a building that has, in fact, negative carbon emissions. So we're creating more energy than we're using. That certificate was the first certificate that was, I think, ever issued, which had a value of -1 in it. So that's your energy performance certificate that goes up in the building. And the project achieved BREEAM Outstanding. And not only that, we believe the occupants were particularly happy with the use. I went back many times, and people were happy to work in that building. So that was basically the test bed, as we alluded to earlier, and it was more of a research-based project really than anything else. And we used the principles and the basis of the information that was discovered in that project for what I think has also been said as the Big Brother, which we can see here. We've already seen some of the pictures, so I don't want to go into too much detail about the various construction principles, but just to say that the image there on the right hand side is a dynamic modeling image, and the school element of that project, which was a school for kids with mental health issues, is at the front of the building, with a large area at lower ground floor, which was for postgraduate training, and then an office area in the existing building, which was also very interesting because that was a retrofit facility where we retrofitted high levels of insulation and more mass to create comfortable conditions within the space. I just would like the photograph, which is a photograph of one of the meeting areas, to just bring your attention to that wall where there is where the screen is shown. That wall, as installed, actually was analysed at the pre-planning stage. So really, what I'm wanting to do now is just quickly show you. So this is the pre-planning analysis work that was done for establishing the comfort building, and the greeny bluey image is the output from the dynamic model identifying that the building during the summer period achieves sort of internal conditions which are temperate and within that sort of 25-degree zone that I was alluding to earlier. But just to bring ourselves back to the end wall. So this is, remember pre-planning. The yellow area on that wall identifies to the architects where we need additional thermal mass. So, you know, we're talking here about criteria being given at a very, very early stage of the process, and then installed and actually part of the final construction. The project, again, hit BREEAM Excellent, and we are in the process now of a post-occupancy evaluation stage, and we've got through the first sort of 8 months of that, and the project is performing extremely well. No complaints as of yet, which is always extremely positive.
Hi, Paul. We're running a little over time, so okay. I was hoping you could.
Shall I quickly wrap it up?
Wrap it up if that's okay.
All right, sorry about that, everybody. Just quickly then. So just very quickly, from the very outset of a project, agree the sustainability objectives and get those in report format so everybody can refer to them. Discussed all the options with the rest of the team and the client. Consider the holistic design approaches. Let's get the whole team working together to achieve the results we're looking for. Examine long life loose fit versus short life lean design. Consider material choices, maximize passive environmental elements, reuse whenever possible, design efficiently, review objectives against the proposal at each stage, design for reuse, and complete a post-occupancy evaluation. Thank you very much.
Thank you, Paul. Sorry for hurrying you at the end there, but
No,
that
no
was
problem.
really good. That was really good. Thank you. Ian, I think, did you want to say a little roundup there? Oh, you're on mute there, Rob. Sorry, Ian.
Yes, I was just going to very quickly come back in, but I need to return to full screen, or can you control that?
Do you need to present something? Sorry.
No,
Or
it's
you...
me.
Oh, yeah, that's fine. Just present it there. Everyone can see you. It's all good.
The postage stamp in the corner. Yeah, I think you know, thanks Rob and Paul, and obviously you've got the message that we all enjoyed working together, and we've found great innovations and synergies by working together in the way we have. I spoke about innovation at the start, and we've heard more about that. But I also wanted to just say, let's not over innovate. There has been a period of lots of, in the 90s and noughties, you could say there was lots of innovation going on in building design, and that without the post-occupancy properly being done, it's very difficult to know whether those innovations are actually working or not. One thing is in thermal mass, where we can actually calculate it, and I see there's a question relating to that. But the other is actually in the performance of the building systems and how they all work together. And I think we've got to rigorously test our ideas before and learn fully from them before assuming that these things have been successful and are reapplying them to the next project. So don't make assumptions there. I could only really talk with confidence about that first project because we've actually done about 3 post-occupancies over its life so far. And we now know very, very deeply how that building's performing, and I've managed to fine tune it. We actually did an Innovate UK 3-year building post-occupancy on a public library that we were very proud of and thought was performing very well. And actually the findings were very rich, but they were also very sobering. Things that we assumed, or in fact were modeled about stack effect and airflow, were actually not performing that well in the atrium configuration. And I think primarily the feedback was that the building management system was not working very well, and the user management regime was very different than what we'd assumed at the start. Effectively, the building manager had gone from managing 1 building to managing 20. And during that time, the building management system just went out of calibration and nobody was bringing it back into line. So the building is performing very poorly for a long time. And the only way around that, I think, is, well, very quickly to sum up, I felt that those kind of key things are really to maximize passive design measures wherever we can. And that's very much what Rob's talking about and what Paul's talking about. And you know, if we're starting with very clear idea about what our embodied energy is and looking to get that down as far as possible, and then doing everything we can to maximize those passive design measures. Keep the building system simple, easy to use and maintain. You know, don't overcomplicate them and rely on the building management system. And then provide the client with a really simple user manual. We do all our, you know, health and safety manuals and all the various post-construction manuals, but actually you'd need to be providing a little booklet for how to use it, the idiot's guide, and then ask them to share that as part of staff induction. And I think that the big lesson for me over the years is to collaborate with the best consultants you possibly can for the best results. And that's what we've hopefully shown you today. Thank you.
Thank you, Ian. That's absolutely brilliant. I think you've summarised it probably better than I would have, so I'm just going to leave it at that. And I'm conscious of time as well, so I think we're only going to ask 3 questions. But I've asked Rob if it's okay if we can just send any of the questions over to yourselves, and then you can answer them in your own free time and send them back, if that's okay.
Yeah, no problem.
Is that okay?
Nice Sunday afternoon job.
Yeah. So the first question is from Celine Hines from Gould Singleton. This was done before the presentations this afternoon. So she's asked, what is the point in making building energy efficient if we are moving to a carbon neutral energy supply?
Paul, I think you should answer that.
Okay, so in moving towards a carbon zero energy supply, we actually need to pump in a significant amount of carbon to achieve that. So if we're actually just saying, well, let's just make our buildings as energy guzzling as we possibly can, we're going to have to create a much larger network and a much larger renewable energy system to achieve that. And all of those elements incorporate significant amount of carbon. So if we can get the end use and get the building itself down to minimizing the input into it or the requirements into it, we significantly reduce what's going to be required in terms of energy network, which is a very positive thing, I think, moving forward.
Yeah, I agree. Rob, Ian, anything else to add? No.
Answer that one.
So the next question is from Kate Miller from BPN Architects. So she's asked, could you give an example of how materials are reused at the end of life once the building has been disassembled?
Okay, I guess I can probably start on that one. And I mean, yeah, we talk about the circular economy and we talk about reusing the elements that go into a building. So what we need to get better at is recording and logging the elements that do go into a building and designing for deconstruction in the first place, so things can be taken apart without having to knock the whole thing down. If you imagine a in situ reinforced concrete building with all the continuous connections and all the reinforcement, there's not a lot you can do to take elements out of that and reuse them. You have to reduce the whole thing to rubble. I think things like BIM and so building information modeling, how we are creating these incredibly good 3D models full of information, that's a great lifetime asset now for buildings, so that when we go back into a building in 20, 30, 40, 50 years time, we're not scrabbling around for the old paper record drawings or having to do testing. We'll actually know what we've got in there. So that's super useful. It's hard to say in 50 years, again, where technology will be and what the material demand will be. We might be in a different place in 50 years. A lot can happen by then. So it's often it's good to kind of say, give it every opportunity to be reused. But often it's 50 years ahead, so you can never categorically say what's going to happen. We developed a project called Ilford Market, which was a kind of a community market where people wanted to grow and sell, grow and sell food to the public. So we designed a very low impact timber structure, all kind of standard sized components. It was a 2-3 story building, but we actually were able to justify putting this thing on just timber pads above the ground because it's only going to be temporarily in one location. And if you get a bit of settlement, you can just jack up one of the columns, no brittle finishes, very low impact, so you can just pick it up and move it. I think we mentioned before in terms of foundations, and Ian mentioned his presentation about the screw piles. Actually, a lot of the buildings we put in the ground, we put in a ton of concrete into the ground that just has to stay there. So trying to find better foundation solutions or reusing foundations as well is really key too.
I might just jump in there and say, to add to that, the building I showed you from 25 years ago, that actually has recycled components in it. We were using recycled timber beams for some of the main structural elements. The paving slabs that formed the ground floor were all removable. They were just bedded in sand on ground bearing beams, or rather on the beams that were then on the piles. The piles in theory could just be unscrewed out of the ground at the end of use, and various other components could just be taken apart. But that's, I recognize, is a pavilion, and it's easier to do that on smaller buildings. So now that we're designing the new Moorfields Eye Hospital building, we're trying to look at all the various components, window components, for example. where do you get curtain walling, which is composite, where you can actually separate out the timber from the steel at the end of life, or the aluminium from end of life. And it's the market has to develop. You know, it's the products have to be developed that we're working with, and it's only by us all making more demand for that, and through legislation requiring it, that the industry will start to change and will separate out these components. It'll make it easier for reuse or recycling. We know that certainly steel is high embodied carbon in its first instance, but then it's actually fairly efficient once you're actually reusing it, albeit all the complexities of sourcing it and making sure it's pure enough and all the rest of it for the job it has to do. I love Rob's return to the Stone Age myself. I think that's quite a radical proposal, and possibly that that kind of thinking will start to take us down the route of thinking more pragmatically about our buildings and the materials we put them together with.
I think one thing we know about stone, you know, no one's questioning its durability. You look around, some of the most graceful historic structures were stone structures, so it's certainly a material that's going to stick around, so we might as well use it.
I was going to say there's quite a few questions on stone. I think that's raised a few heads, so you're going to have a lot of questions sent over to you for that.
Right.
I'll just finish on I think it's a short one, but we'll see, as our last question. It's a question from Andy Ross, and he's asked, what tools do you use to calculate embodied carbon?
So I can start off on this. I mean, there's a load of data available in terms of embodied carbon by weight of certain materials. There's ICE database, Bath University database, and these numbers of embodied carbon, they're quite complex numbers to calculate because they take into account input materials, processes, transport, things like that. But generally, EPD, so European Product Declarations, will also give values. So really, there's loads of kind of fancy, whizzy tools that do it. Just work out the weight of material you've got and times it by the embodied carbon, and it's just another metric you can get. So it's actually reasonably simple. And for more complex elements, composite elements, so maybe more the architectural elements, bits of facade, you know, the supply chain doing a lot of work to understand their own supply chains and embodied carbon of all the materials and processes that go into their products. So it's something the industry is getting a lot better at, and there will always be debate and argument over the certain values of things and what you should assume. But unless we start doing it and coming up with real metrics for real buildings to be able to compare, we won't move forward. So I think we just have to sort of jump in and do what we can, and you know, it just gets finessed over time once we get more and more data. But I think, just to repeat, really some of the key messages that come from the very basics is that the more low carbon materials you use, the better. The more efficiently you design, the better. And the more buildings we reuse, the better. You know, we shouldn't be scared of building reuse and reanimating buildings just because it's easier to knock it down. I think we should do more of that.
Yeah, I agree as well, because we do a lot of that at our practice. We're reusing a lot of the buildings in the Drury Quarter.
Yeah.
So that's absolutely brilliant. So I think that I'm just going to leave that as the last question, if that's okay. But I just want to say a big thank you to Rob as well, because Rob, the idea of this seminar came from Rob approaching me at an archetype lecture. So it feels like a long time ago, but it probably wasn't.
Yeah.
But I just want to say,
back in the normal days.
I know, yeah, out of this craziness. But yeah, thank you very much to everyone. Matt, was there anything that you wanted to say just before we all leave?
Yeah, so a big thank you to our presenters, guys. Thank you so much for everything that you've given us. It's been a really interesting talk, and I think out of all the 75 of us who are still here, even though we have run over, thank you again. So And then a big thank you to Katie and Georgie for handling the questions. That was well done. So thank you very much. Guys, I don't want to keep you any longer because I'm sure out of everyone's day, this has probably been the last Zoom stroke Teams meeting that you want to be on. So, just wanted to say quickly, please do follow us on Instagram, LinkedIn, Twitter, all of that for some of our latest news and updates. A couple of events just to highlight quickly before you all hit the leave button. The Birmingham Architectural Association is presenting Resilience. We've got a key speaker, Diane Hoskins, the co-CEO, of Gensler. So she's talking on Thursday, the 25th of June at 4 o'clock. Again, check our social media regarding that. And again, we're doing a design competition calling All Creatives Home. All around the showcase and strong connection to home. The submission deadline for that is for the 13th of July. Again, please just check social media for that one. And last but not least, but we are, if you, as BAA, we feel it's, we want to share and be available to our architecture and design community. So if you do have any job postings that you want to share with the wider community, please let us know and email the BAA team at baa@brumarchitecture.com. And just as a final thing, yes, to all of the questions that we've had, this recording will be sent out to you if we have your emails. So that will all go out. And a big thank you again to everyone who came today. So and again, thank you, Paul, Rob, and Ian there for presenting such amazing topic, and it was really good. Really enjoyed it myself. So thank you again. Thank you all.
Thanks, guys.
Thank you.
Thanks.